And we're DataHeroes. I'm the chief scientist of DataHeroes, Eitan Netzer, and we're going to talk a little bit about how you can use Coreset to improve your machine learning models, both in building them and in maintenance. Okay, so a little bit about me. You were asking about your degree, so there you go. I have a BSc in computer engineering from the Technion. I did my master thesis on how to use brain signals to teach AI systems. Been data scientist for roughly 12 years, and had the pleasure to teach a little bit about AI and data science, both in the Technion and a few other places. The other thing that is not written over here, I started my PhD on a topic that is named as Coreset, never finished it, and stopped it to do DataHeroes, and we're gonna talk a little bit about that and why I prefer to make it a product and not my PhD. So, building a Bell model using our framework. We provide in DataHeroes a framework for building better and faster machine learning models. The way that we do that, we know how to compress your data to reduce the size of the data using a small subset out of the data in such a way that we don't lose statistical information and don't lose edge cases of your data set. So whatever you used to train on your full data set, now you can train on a fraction of the data, giving the same results. Now, we're not replacing your original stack of machine learning tools. You can keep doing your labeling, cleaning, training, hyperparameter tuning, whatever you used to do with other frameworks and other tools. You can keep using them as we go, and you can keep install DataHeroes at the end of this lecture and see how everything goes. One more thing I wanted to elaborate. Blumberg Capital is one of our investors, as well as AI Fund and Alumni Ventures, and we thank them for their support. Okay. You people in the way were blocking the signal. Okay, so how we do this reduction of the data? So of course, it's from big data to small, good data. In a nutshell, what we're doing is we start with the data set and the given cost function we want to optimize. We compute per each data sample instance, we compute the importance of that sample. You can think of importance as the uniqueness or how much that data point is affecting your model. Okay? As an idea. We construct using that a probability space. Using that importance, we construct a probability space. We sample according to that probability space and assign to each selected sample a corresponding weight. And now, once we have that, we can compute our model or cost function using that subset with weights and get the same model that we used to get with the full data. I know that in words it's a bit tricky, so let's look on the illustration. You can see over here on the top, when we're using the full data set, there's a lot of data. It's a mess. As a data scientist, you want to get into your data and actually know him. It's a bit hard.
Are you dropping data or are you just waiting?
We are selecting data. Because it's a subset, you can say that we dropped some of the data, but because we are using weights, there are another way that we take them into account. We're not completely reducing them. Okay, they're taking it out by using the weights. Okay, so we have the full data set. What we've done with our process, that we compute the importance of each data sample. We have that, we build a course, we build our probability space, we selected a subset out of the data, assigned a corresponding weight, and we got this over here. Now, as you can see, I'll let you see because I'm blocking the image. As you can see, this is a much small subset over there comparing to the original data. And due to the weights that were given, we compute the same decision boundaries that we have over here, and both images are the same, they are computed. It's not a marketing plot, that's a true plot, that we have the same decision boundaries for both full data and the Coreset. So whatever you wanted to compute using your full data set, you can do with the small data set. Now, after we've seen the visual illustration, a little bit of a use case that we've taken a data set with roughly 600,000 instances. And when you compute logistic regression using the full data set, you have an area under curve of roughly 0.78. Okay, that's pretty much the area under curve that you're getting. If you randomly sample 1% of the data, you really hurt your model. You get down to 0.725 area under curve. That's pretty bad. We had to go up until we sampled 15% out of the original data to get roughly to the same amount of area under curve that we had before.
Do you assume anything about the distribution of data?
We know the data and we know the cost function. We don't assume anything else. Now, using DataHeroes, the way that we selected our subsets, using the same 1% that was doing horrible over here, we got to exactly the same result as using the entire data set. Okay, so just a second. So whatever you used to do on the full data set, now you can do on the small data set, and it's much easier, both cleaning the data, running hyperparameter tuning, everything is much easier. Yes, also, but from now on, let's keep the question to the end. Yes, also.
I wanted to ask about the importance. It sounds like something in the spirit of SHAP or something?
In the spirit of?
SHAP score?
No, it's not a SHAP score, because in SHAP, it's for the features. It's something that is out of the scope of the lecture. It's too mathematical for this scope of a lecture, but you can always ask us later. We'll have our email in the end. Okay? Great. So now after we introduce ourselves to Coreset, we were already invited to PyData roughly around September, and we already talked about Coreset and how they can help you to clean your data much more efficiently. Okay? So in this illustration, what you see, we've taken a data set. We computed the importance of each one of the instances. We've taken instances that had a correct label. You can see those one in blue. And we've taken instances that the label was wrong, and we computed the distribution of their importance. As you can see, when you look on the distribution of the clean instances, their importance is much lower. And when you look on the distribution of the of the noisy labels, their importance is much higher. So it's a pretty good way to split your data into clean and non-clean instances. Okay, so that was nice, but we want to see that in real life. So we've taken the well-known data set known as Imagenet, and we computed the importance of the instances over Imagenet. And apparently, it's quite noisy, even been done a lot of work with it. Everybody's using Imagenet. There's a lot of noise in Imagenet and long labels. Okay, notice that the results over here are not the results of the machine learning model thinking those are missiles. This is the actual label given in the data. Okay, so you can see in the first line a few examples that had a low importance. We can all agree that those are missiles. That's pretty easy to see. Over in the bottom row, you can see one that had a high importance that actually incorrectly labeled. Those two hopefully are easy to spot that it's wrong. This one is confusing at first, but notice that it's not a missile. It's it's a rocket for a space shift. So it's nice to see that the math know how to identify that we had a few mistakes in the data that were labeled and given as gold standards. And we've taken that process and we've done the next experiment. You can see on the plot on the left, for every 100 images that we ask using the importance, we ask for high importance images. We manually viewed the images. And you can see that in the y-axis, how many were labeled as we were going over the images. So as you can see, using the Coreset and importance in order to clean your data set from and fixing wrongly labeled images, that was getting quite high. On the contrary, when you do that pretty much randomly, as you suspect, it's very hard to notice that you have any problems in your data. It's going very slowly. Now, of course, the better data that you have, the more you clean it. The plot on the right shows you that the accuracy of the model is getting better and better as well. There's no surprise there. Okay, so up until now, everything I already told on this kind of a stage of how to clean your data using Coresets. Okay, now we want to talk about something a bit different. How we can use Coreset to maintain your model and avoid data drifts. Okay, so, we cleaned our model, we have a good model, we moved into production, and the one thing we all try to not even ignore, not to avoid, to completely ignore is the fact that the data keep changing all the time, and the model that you had working great a month ago is not updated with the new data coming in and need to be updated. Now, there are enough people and companies talking about how to detect drifts in your model. We're not going to talk about that. That's not the purpose of this talk. What we are going to talk about is the following. So in order to avoid your drifts, basically after you detected it, in order to avoid it, there are two things that you want to do. You want to clean up your data, the new data coming in, you want to clean up the mistakes that were done. We already talked about how Coreset can help you clean your data coming and make it much more pure and reduce the noise in your data. The second problem, sorry?
You define data drifts?
No, I did not define data drifts. I talk about it generally, about the fact that every time that you have a model up in production, after a while, your data keep updating and change, and now you want to update your model with the change that happened in your data. So we already talked about how you can clean your data using Coreset. Now we want to talk about something different. There's another problem when you try to update your model, that in order to avoid drift, you would like to update your model frequently. But cleaning your data and updating your data both require a pretty high budget to do that. And if you want to keep updating your model, it's a problem because all the time, the training time is growing more and more. So can we use Coresets in order to reduce the training time that we're computing? So there is a unique data structure called Coreset tree that we're going to discuss about. Okay, so imagine that you have your data, you split your data into batches, okay? In this case, we have our data x1 to x21. Okay, we split into batches, and now we already know that we can compute a Coreset for each batch. Now, the next thing we can do, there's a nice property of Coreset. We can take two Coresets, unit them together, and compute a Coreset over them, and get another layer of Coresets. And of course, we can keep doing that again and again and again until we get to the root. And now everything that you used to compute using your full data sets, you can compute and get the same result using the root C7 in this example, getting the same model as if you were training the entire data. Okay? So now we want to talk about what will happen when we get another batch of data. So the first thing we're going to do, you're going to put in the corresponding place in the batch, the new batch coming in that we want to compute. And now in order to update our model, all we need to do is to update the path C5, C6, and C7, which is a fraction of the computation needed to recompute the entire model on the entire data. And now you can very fast compute a new model using only C7, getting the same results as using the entire data set. Okay, so we have a little bit of a demo for you guys, okay? We ran most of it because it's take a while, and I don't want to sit like this for a long time, okay? So I'm going to go over it briefly. So first of all, in this demo, we have a few parameters that are important. Most of them are not critical for everyday use because are pretty familiar with you guys. For example, the model parameters. The ones that we are using is the Coreset size and the chunk size that you've seen in the previous slides regarding Coreset tree. Okay, so we imported the data, have some important help function that's not very interesting. And now we have a data that is 60 million long. Okay, so as you can see, computing a model, which is a logistic regression model, on the entire data set took roughly 40 seconds to run. Okay, Now, you can see over here that we defined a Coreset tree service for logistic regression. As I mentioned earlier, it's important for us not only to have the data, we also need to know the kind of cost function or model that you're trying to learn. And we build a tree using that. And as you can see, building the tree and computing a classifier over the root of the tree took roughly the same amount of training on the entire data set. Up until now, not very exciting news. But, and they got roughly the same score in terms of accuracy. And now we want to add more data, okay? Okay, this one will take a while, okay? We're adding more data and training on the full data set with the added data, meaning that we have more than 60 million samples right now running on the background. We chose one with not a lot of features, so this will not turn into an exercise workout that I'm doing here, squatting over here. Hopefully it's done already, not yet. It will take a while. Ilya can finish his riddle if he wants to.
Finish my what?
You can finish your riddle from earlier. We need a time gap.
May I ask you a question?
Yeah, question.
Yeah, a question is a great time gap. Yeah.
You've tried that on all different kinds of data sets, models, I mean.
Okay. When you say model, I say cost function. We don't have that for every cost function available in the world. Okay, we are working on a few of them that we don't have yet. We have most of the classical machine learning. We don't have everything yet. Regarding the data set, we work on the feature level. So we don't care about how is your raw data coming in. We care about the feature embedding that you have in the end. So if you're talking about NLP, computer vision, or anything else that you can embed into a feature vector, we are there. Great. Is it done? Great. Okay. Great. So as expected, it took almost 30 seconds. Now, if I'll do the same thing using the Coreset that I built earlier, all I need to do now is partial build and add the new data coming over there. And as you can see, it took 7 seconds. I didn't have to gap the time over here. Now, if I want to compare the results, you're getting roughly the same, exactly the same number in this case. Okay? So that was very convenient for us. Just a second. Just was very convenient for us working and updating our data. Yes?
What happened in the model that the results before we were the new small set was so much lower than the results than after?
Sorry, what? Why?
The previous result was 17.
That was like the fifth digit, if I remember correctly. And by the way, in many cases, we're actually getting better results from the original one because, for example, scikit-learn is optimized for medium-sized data. And a lot of time we get actually better results using our method. If I was...
Is asking why the model after the data update?
That's...
Yeah, why it went from 79% to 87%?
Okay, sorry, I thought you asked.
Too good to be true.
Okay, that depends on... That depends on the time, because you added now more data, and now the drift is less, the new data coming in is updated with fresh data. That was not the purpose of that demo. Okay, the demo was more for time building.
987 looks a little big.
That was not the point of the demo. The point was to show the time constraints. If you want to talk about that, we have this that will be more the one after this that will be more efficient to talk about. Okay, so the training time. So we just showed that if we want to frequently update our model, okay, if we go with an additional method of adding up all your data coming in using the full data set, we start with having 0 new data coming in, and the x-axis is as the data getting larger and larger, from 0 new samples to 20 million samples. The y-axis is the time of training the model. So as expected, when you do the additional using the full data set coming in, the training time grows linearly as it goes, and sometimes the gap over here and start to play with the RAM a little bit because you don't have enough space on your RAM. You need to shift between RAM and other spaces. On the contrary, when you use the Coreset tree, you can see that the update time is pretty much fixed. Actually, it's not fixed. It grows logarithmic in the log, but it's hard to see. And as your data gets larger and larger, it doesn't matter because of the Coreset tree structure. Yes?
Excuse me if it's a dumb question, because I'm not an Android developer, I'm a PM. But using Coresets to have more catastrophic forgetting. Sorry? If you use Coresets to have more an effect of the catastrophic forgetting.
What do you mean catastrophic forgetting? We're not, that's the nice thing. We're not doing an online learning or looking just on the last time window. The tree is growing, and we're not forgetting. Okay? Unless you want that as a feature. Sorry?
In some sense, you compress it.
In some sense, I compress the data. It's not lossless like zip compression. It's a subset over there, but in some way I compress the data. I prefer to say that I'm not compressing it. I'm selecting it according to the cost function. So it's pretty close, but I prefer to say that I'm selecting it, not compressing it.
Yeah. Question about this. What happens when the bottom is small?
Those kind of engineering questions is for the guy sitting 2 rows behind you, and that's not the right time right now. Okay, so we have that. We show that we can effectively reduce the time to compute, make it affordable. Now, does it even worth it? So that's the same experiment from before. Now, the only difference now, the y-axis is the accuracy. So as you can see, when both models started, we had the blue one updating fast every 10,000 samples. It's being updated with a fresh model. The red one is updating much slower using the full data set with 200,000 samples. So as expected, when we start, both of them are pretty much similar in results. But as time goes, the drift starts to be more and more effective. And after a while, it's becoming of an issue. As you can see, after a while, the blue one, updating every 10,000 samples that now we can do because it's cost effective, is getting much better results than the one that we slowly update because we don't have the budget for training that. Okay? Now, we already talked about how you can reduce your budget. We talked about how it can actually help you getting a better model and having a better results. And people sometimes forget, but that's that's also important. Sorry. That was not the right time. The carbon footprint, using DataHeroes is a lot greener, much better for the environment because of the reduction in compute time. The carbon footprint, is actually roughly, 10 times less than using the full data set. So it's also better for the environment using Coresets. Okay, now the one that I had, what's going on with me today? Okay, so we're not the only one that think that Coreset can really help. Okay. We're not the only one that think that Coreset can really help building better models and faster models. Professor Andrik shared that vision with us, and he also put the money where his worth is, and he's one of the largest investors in DataHeroes, and he shared our vision towards Coresets. Okay, so I want to thank you guys for hearing. We have a new version that came out literally today. Okay, you can either use the link or use the QR code. Okay, if you have any questions, both my email and Liran that's sitting over here, which is the engineering question are towards him. So
Go for it.
Go for it, exactly.
And the deep mathematics, of course.
The deep mathematics is for me. Okay, no problem. We'll work with that. And I want to thank Blumberg Capital for having us and hosting this event, and PyData, where is PyData? And the PyData also for organizing this event. And thank you very much. And now if there are any questions, now would be the right time for it. Yes, Oz. Just a second.
I didn't understand, I'm not sure if is your model or technique model free? I mean,
no, it's not model free. It's based on the cost function. If you decided that you want to train linear regression and tomorrow you want to use the same results that we are providing you to train a k-means, I'm not promising anything. I'm assuming that you know the cost function ahead of time.
Not exactly the cost function, but the model. I mean, the model and the cost function.
Okay, the feature extraction, the model, and the cost function. Yes, yeah, that's correct. Not only the loss. On the feature extraction, we can do sometimes a little bit of, but we can reduce that sometimes. That's not the right place for a wall. We can work with that sometimes, but in general, you need the model, the feature extraction, and the cost function.
When you will give the lecture about the deep mathematics of the
I'm not going to give the lecture about the deep mathematics because it's not the right form for that. You can always ask us and get like a gazillion articles about that, and we can talk about it. We can do that on a nutshell offline. Yeah. Yes.
Yeah, the opposite question. So you mentioned you studied a PhD and your brother studied. Yeah, how like can you elaborate a little bit how you said how you saw the opportunity?
How you saw the opportunity? Yeah, sure. Sorry, I forgot the video is there. He was asking about why did I stop my PhD for pursuing this? What was the opportunity that I saw? Yeah. Okay. So prior to doing my PhD, I was working in the industry, doing freelance and consulting work for companies. And when I saw a bunch of problems, and I saw this deep mathematical topic, I said to myself, most of the time is wasted on waiting for computation and having too much data that I don't want to clean it, not because it's cleaned, because I don't want to clean it. So this was the opportunity that I found, combining both the mathematical end and the more practical end of it.
Yeah. I'm not asking about the math, but I'm just wondering if it's not intentionally intensive to capture the importance, because you go point by point. That's do something with the cost function, even without the math.
That's a great question. I'm repeating it for the video. He was asking if the computation cost is even worth it, because it sounds like computing the importance itself sounds like heavy lifting. So first of all, if you're going to compute one time your model, one time and one time only, don't use us. I agree with that. That makes sense. Even though when you saw that we were building the Coreset tree, we were actually faster than working on the entire data set. So first of all, you keep updating your model. Either it's hyperparameter tuning, adding more data, cleaning your data, and rerun your model a lot of times. And because of the Coreset tree, it's a lot more effective, because when you keep updating it all the time, it's much easier, and you don't need to recompute the entire computation done for the model. You just need to do it for the right sample.
So in each iteration, you actually calculate it's efficient, because for each iteration you calculate the Coreset for the delta, for the new data that is coming. You already have something that's...
Exactly. That's one reason, because we can split it into small batches and work in merge reduce. That's one reason. The second reason, when we build our probability space, for us, it's enough to approximate the importance. To compute the exact importance, it's very hard. The computation cost over there is very hard. We are approximating it. And when we approximate it, we can do much faster than computing it.
But will there be a drift in the probability space itself with the data?
The drift of the data will always be there. Sorry. He was asking if the drift on the data will not remain there. Yeah, the drift will remain there. We are presenting the data that you have. If you have a drift in your data, I'm not magically disappearing it. What I'm doing is allowing you to recompute your model before that drift becomes catastrophical, and then your model is giving you more nonsense than real answers.
Yes, I would like to understand the process. You are creating Coresets for your data, not with the framework. The framework is not creating the Coreset.
No, the framework is creating the Coreset. The framework purpose is to compute the importance, create the Coreset, maintaining the Coreset tree, of course, and you get a result. What you get in the end, you can either use us to do a fit for your data. We have that built in, but you can also get from us the selected samples and their corresponding weights and do that wherever you prefer. If you want to move to another platform because we don't trust us, that's fine. Use it over there, no problem.
Okay. Is this framework supports also JavaScript?
No.
No?
Take questions.
Does the framework support JavaScript? No. Yeah.
What type of loss functions you can handle?
Right now, we support a few of them, not all of them. We support k-means. Right now, mostly classical machine learning cost functions, okay? As you guys imagine, deep learning is a bit more complicated than other ones. We're working on it. We're soon to have that. Right now, it's in research mode. It's not yet available to the general public. We have most of the classical used machine learning cost function because a lot of, for example, I don't have a Coreset for naive Bayes because that's not, you don't need me for that. That's pretty simple to do yourself.
One question, but what about R1, like R1, R2, not R2? I can ask you in the next.
Okay, no problem. Okay, so later.
How do you, if you had an unfruitful first randomization or whatever way you choose the samples, you demonstrated like the first Coreset, second Coreset, etc. And by some strange coincidence, or perhaps it's a byproduct of the gathering of the data, somehow the Coreset, a situation will occur which it's like Simpson's paradox, where the first Coreset misrepresents the data in some way, the second Coreset misrepresents the full data in another way, and then the combined will not do justice to the, if you have a full data.
That is a great question. I will shorten it because that was a long question. So for the video, what will happen if the initial Coreset that you computed was wrong? Okay. So if we were randomly selecting our subset, we have there is a high chance of probability that will happen. Okay? The nice thing about Coresets is they are mathematically proven with guarantees. So as long as you select a Coreset that is big enough as proportion to your VC dimension, and you are, if you want to be really safe, you repeat it more than once, you build a probability space that the probability that will happen is lower than the heuristic tools that you're already using, because that same problem you described, that the random seed, that the initialization is very bad, exists in everything that we use already. Okay, the nice thing that we have a guarantee when it will work. Okay, so, and another nice thing about it, I did not talk in depth into the definition of importance, but it's not just for the optimal model, okay? It's for every model of the hypothesis family that you're trying to solve. For example, logistic regression. It's not just for the optimal line going over there, it's for all of the possible hypothesis models in that family. So we have a stronger guarantee than randomness, because even if you're choosing the worst one, we'll still have a guarantee of an epsilon error that you can control by getting a smaller or larger Coreset size. Non-burning questions, yeah.
Hi, thanks for the lecture, first of all.
Sorry?
First of all, thanks for the lecture. I really enjoyed it. I'd like to ask, are there any downsides?
Any downsides? There is a downside. Okay, if you have a small data set, a very small data set, and you want to use the Coreset tree, we do have some overhead that it's not worth it. You can see that already. It doesn't work if you have a very small data set. If by mere chance that is unlikely to happen, there is some probability to the building that we're doing, there is some probability. So if you have like a tremendous reason not to use probability methods in your stack, then there is probability over there. But I think every solution I'm familiar with today has some probability into it. Except the overhead, if you have small data sets, I cannot think of another reason not to use it.
If you want to use deep learning,
Don't worry, we'll solve that very soon.
We will.
Yeah.
I'm interested, how would that work with time series analysis?
When you say time series analysis, sorry, he was asking how it will work with time series analysis. In my mind, what I care about is the features that you're going to build after from that time series and how you're going to organize your data. Once it's organized in a matrix and using one of the traditional models and optimization methods for computing something, it's the same. How would logistic regression handle time series? You will organize the data in a way that that it makes sense for a time series and then run a logistic regression. It doesn't matter. Okay, same goes here. What we are doing is promising you that you'll get the same cost function as the cost function that you used to work with the logistic regression. We're not doing anything else.
Have you tried comparing the time savings of the Coreset tree to the time savings of using a online learning or transfer learning framework?
We have not tried that because that's two different. Have we tried to compare our time runs to transfer learning on online learning? We're not, because there's a big difference. Because online learning and transfer learning has the potential to be biased by new data coming in. So if for example, you have a great transfer learning method, but you only saw a very specific new data coming in and you don't keep using your history of how you got there, you'll be very, very biased towards new data coming in. So instead of, you might be more fitting to new data coming in and so-called avoiding the drift, but you have the other problem that now you forgot your past and things that you used to know and used to work for you are now not as working as good, both for online learning and for transfer learning.
All right, last question.
So, another question. Is the problem with the data in the mathematics or in the applicative side?
That's out of the scope of this lecture, sorry.
There's no problem.
Okay.
We exhausted the not-burning questions.
Okay, so thank you very much.